Okay, so I'll just share my screen, and today we're going to talk about the comparisons of all the different quantum hardware that's available. It's a very difficult comparison to draw, I might add, and we'll see that. So, slide from the beginning. So, yeah, the comparison of the quantum hardware. And I'm basically going to go over why it's so difficult to compare quantum hardware as opposed to classical hardware, where you've just got benchmarks, basically, which are enough in generally, anyway, are enough to tell you which, computer's going to compute faster, and because they all essentially work the same way. Whereas in a quantum world, it's very difficult, if not impossible, to actually put it all together. And there's a school of thought that we're not at a stage yet where we can properly compare them anyway, because because we're only entering the NISQ era. So you've got NISQ as opposed to fault-tolerant computers. So fault-tolerant quantum computers are the real deal, where you've got pure qubits or very, very little noise. And we're nowhere near that. So we have, most quantum developers are now writing for the NISQ era. But all of the algorithms, fate may have it, or maybe it's logical, but all of the algorithms which run on NISQ technology are heuristic in nature. So that means you've got the exponential algorithms where we know we will get exponential improvement, like Shor's and I think Grover's, or Grover's may be polynomial, but we know it's going to be exponentially or a really good deal faster on a quantum computer. But they are all for FT quantum computers. All the algorithms that we can run now on NISQ are actually heuristic. And heuristic algorithms are where we don't really know. We have a good indication that the quantum algorithms are going to be faster than the supercomputers, but the jury's still out, if you like. So in some ways, we can't even test which fundamental hardware is running better, but we'll get into all of that. So I'm going to talk about, let me get my pointer up. So I'm going to talk about how we compare quantum hardware and how we don't. And I'll immediately say we don't compare it on the number of qubits, which of course is how people first, and in fact still, describe computers. If I say someone's got 1,000 qubits and someone else has got 4, then one automatically assumes that the 1,000 is better. But of course, 999 of them could be on quantum error correction. And like, for instance, Microsoft with its topological qubit, they literally only have, it's either 4 or 6 that they're working on at the moment. But they work on the majorana fermion, which means that the noise is substantially better. And we'll get to that a bit later. I'll talk about quantum vendors. I call them quantum vendors. They're platforms, and it's becoming very popular. And like with Amazon Web Services, they are platforms where developers and ordinary individuals can log on and use a variety of the different hardware. Now, this obviously has an appeal. because, for example, quantum annealing is essentially better at quantum optimization problems than gate-based quantum computers, although even that's up for discussion. But you can seamlessly move between ion trap, superconducting, through different technologies on the vendor side. So it's very good like that, and it makes a lot of sense for them. Like, for instance, IBM, even though they have their quantum experience, it's all just their own superconducting qubit. I don't believe that they, and I may be wrong here, but I don't think that they have different vendors on their website, which could lead to problems later, because the race is on. And now the race is on. Let's look at these. I've come up with 5 of the main qubits. That's super technologies, superconductive qubits, trapped ions. They're certainly the 2 in vogue at the moment, but that doesn't mean that they'll be in vogue in, let's say, 10 years' time. And then you've got photonics, which is running at 100 miles an hour. Quantum dots, amazing technology, very good for memory, perhaps subject to scalability issues, which we'll discuss later. And then the topological qubit, which is like Microsoft. So I'll talk about these 5. I'll very quickly say how they work. I won't be dwelling on that because I want more to talk about the vendors who have gone that way, and then the inherent issues they have and what they're good and bad at. So it's very interesting. Okay, how do we compare quantum performance? Well, and don't worry, you'll get this in the notes. If you can't see it out, I'll be sending you the presentation and the recording so you can see. Now, this is from the Boston Consulting Group, so a very reputable authority site. Now, this is a couple of years out of date, but I still included it because it shows the different areas that we need to understand. The physical qubits, the lifetime of the qubit, the gate fidelity, that is where the gate does what it's supposed to do, and how long it, I'll put these spotlights on, and how long it takes the operating time. And you can see, like for instance, with the qubit lifetime, with superconducting, you've got, it's in microseconds before it decoheres. Whereas with trapped ions, you've got, and I think I might say 50 seconds, which of course will be more now, but it's interesting to see that huge difference. And I'll talk about in a couple of slides further on about what each technology is good at. And it's amazing how some are good at one thing, but then, like life in general, bad at another. And the connectivity, that's very important because you see, we want the qubits to talk to each other, but we don't want them to interact with the environment because they will obviously collapse. So that's a very, very difficult thing to do in the superconductive world. Photonics have no problem with that whatsoever. And they say that's a very good way that they're going to be scalable. And Xanadu are doing a lot of work in the photonics. And it's difficult to compare a photon with an electron, because everything's different, the spin, the polarization, etc. and photons don't interact with each other very well, but they the connectivity is very, very high. And the scalability, you can see that they're talking about photonics and silicon base, which is your quantum dots, as having real scalability advantages. And here we have the maturity of the technology. So even though no technology is mature, you can see that superconducting and trapped ion are far more mature than the other industry, the other technologies which are just beginning to catch on, let's put it that way. So that's a very interesting slide to read. And then we talk about here the different players and the different things that they offer. Like we have the end-to-end suppliers, so they actually do it all. And here you've got your IBM, Google, Regetti, Microsoft, Alibaba, DWave. They are actually doing the whole thing themselves, although I think there is a tendency now to split up the supply chain, if you like, simply because one will get better performance that way. And here we have the hardware and systems players, and all of these are potentially moving into becoming end-to-end providers. And then we've got the software only type people as Zapata, and then a great company from England, the Cambridge Quantum Computing, which was actually started by Elias Kahn, who was talking to Stephen Hawking, and Stephen Hawking said to him, "Why don't you open your own quantum software application development company?" And so that's where that sort of came from. And then you've got specialists in certain areas. Q Control is from Sydney or Melbourne, Michael Steerkel or something. And they're working on specific aspects, and they're working on controlling the qubit. So we've got different players doing different things. Now, so let's start off by saying how we don't compare hardware, quantum hardware. We can't compare it by the number of qubits, as I mentioned before. And we can't even compare it by the fidelity of the quantum gates, because that's very, very difficult to measure and is misleading. And we can't go measure by the synthetics of the qubits, which is actually, IBM have called this quantum volume. It's actually the combination of the two. And you'll hear quantum volume being used an awful lot as a parameter that one can compare different hardwares from, but it really isn't the right way to do it. And what is the right way really is to run an intermediate solution is to run a basic algorithm on all of them. And this is very easy to do. And one that was put forward by, and I can't remember his name or the company, I really can't. But he was saying, look, just run the Bernstein-Vazirani algorithm on all of the different technologies. And with something like Amazon Web Services, it's very easy to do. And whilst not being perfect again, because you can't, it's not really a fair way just by running one algorithm. You know, you really should be running hundreds of them, but you have to remember we're at the beginning of all of this. So soon, there will be companies that will run 100 on every one, quantum applications on all of the different platforms. And then we may, or we may not, because of the heuristic nature I was referring to before, we may see significant differences in operation speed. The other way is to actually, as I say, to grow the number of algorithms, etc., that you're running on the different technologies. Now, my good friend Martin Mackin from Quantum South in Uruguay, the guys have been out of 800 developers for the Airbus Quantum Challenge. They're shortlisted for the last 5, and hopefully in December, the win will be announced. But I asked him, because he has run his optimization software, and that's a QAOA algorithm, so quantum approximate or quantum approximation. I've got, I can't remember. Optimization algorithm. There's VQE and QAOA, and he's run that on all of the platforms, and he said that there wasn't really a difference in operating speeds, but he's not surprised by that, and it's not giving us that is not telling us anything. Again, I get back to the heuristic algorithms, and that's where we run algorithms which mathematically are indicated should run better on a quantum computer, but because we're only at the NISQ era, we can't tell, if you like. So he certainly couldn't tell in his software, but there are things like the connectivity between qubits. So rather than, at this moment in time, in the NISQ era, rather than being benchmarked for operational speed, accuracy is more important. So, and that's why we get back to the fidelity of the quantum gates and the number of connections between the qubits. So it's interesting, but it's a difficult measurement to undertake. So let's have a little bit look at what we should be looking for with these device requirements. Now, the important thing is we want the qubits to interact. In fact, we have to have the qubits interacting with each other, but not the environment. And some can do this very well, and some do it very poorly. And I will get to that a little bit later on as well, especially when we talk about photonics as a technology. Now, you see, with the superconducting, the controllability is good. So controlling the qubit, because in a superconductor, it's actually, you're working with atoms, and by that very nature, rather than subatomic particles, they're easier to control and to interact with other things. So that's the controllability. But the coherence time is very poor, as we saw before. There have been improvements, but even so, the coherence time, which is how long the qubit is acceptable, can counteract the noise, it's very, very poor. Trapped ions, on the other way, And their controllability is poor, but their coherence time, as we saw before, is exceptional. So that is very interesting. And we'll just quickly mention the quantum brokers. So we've got the Amazon Quantum Solutions Lab. They're using their large installed consumer base who are currently on AWS and offering the quantum solution as just another solution for them. So they're out there getting, and Quantum South are on in the Amazon Quantum Solutions Lab and testing their software along with many other developers on different areas. Now, I don't know how expensive it is. You do have to pay for it. So I have no idea how much, how costly it is. But if we look here, it will say, Amazon Quantum Solutions experts will work backwards with you to deep dive and learn about the science of quantum computing, develop and benchmark new algorithms and solutions for you. Very important service. And then make it as good as we can, basically. So it's again is interesting stuff and is the way to go. And here's the partners it has at the moment, and you can see a few very big names there: Regetti, QC, Xanadu, so and Zapata. So we've got Iron Trap, Superconducting, and Photonics, and I'm not sure what the others are, but a couple of them may well involve different technologies. So Amazon are being very clever about it and covering the market, if you like, because don't forget the race is on. Whichever technology proves itself indisputably to be better than the others is obviously the one that's going to take off. So that means IBM and Google and Microsoft are all betting on different horses, if you like to use that analogy, in the Melbourne Cup week. So it's interesting to see how that's happening. Now, Azure Quantum is the Microsoft experience. So basically the same thing as AWS. They're getting people on to use their Azure product. And we can even see some of the same names here. They've got Honeywell, IonQ, and one Cubit, and Toshiba, which hasn't been heard about much in this world. So we're getting more and more entering the market, and again, different technologies. Honeywell, I'll be mentioning later, in the trapped ion world, are really promising amazing growth, and they've just come out with their as in this week, with their new quantum hardware, the HO, I think it is. Okay. Oh, and then we've got Leap from DWave. So and they have, which I'll be mentioning on the next slide or very shortly, they have what's called the advanced computer architecture. So and DWave are doing a lot of work in quantum annealing, which is a different logic to the quantum gate-based programs. It sort of finds the lowest eigenstate for a data set. Okay, let's have a bit of a dive into superconductor qubits. So they're solid state electrical circuits. There's no moving parts, if you like. and the superconductor means no resistance to the current, and they're based on Josephson junctions, where it reduces it to two states, two energy levels, quantized energy levels. And within superconductive technology, you've got different types, many types actually. So not only have you got banking on the technology, you've then got banking on a way of implementing that technology. So you've got the Transmon qubit, which is from IBM, which works off this quantized energy levels, and it reduces it to two orbitals, which are your ground and excited states. So the superposition is between those two states. If you think of that like two planets orbiting the sun, but when they, oh, sorry, one planet orbiting one electron, one planet orbiting the sun, but it's somewhere within Earth orbit and Mars orbit. So it's in between these two states. And that's how we measure it. So it's amazing technology. And then the flux qubit is where the current is going clockwise or anti-clockwise, and that represents 1 and 0. Again, it's always a case of representing 1 and 0. Now, something that superconductive qubits do poorly is what's called the nearest neighbor issue, and that's where qubits are talking to each other. These qubits are actually put on to a chip that which is basically what Regetti does. So they manufacture the quantum chip integrated circuit, and this circuit goes on that. But once it's laid out, you can't change how they all talk to each other, which qubit is next to which qubit, because obviously, depending on the size, if you're talking 32 qubits, it's not that big a deal, but when you're talking hundreds of qubits, it's going to be a real issue. So that's physical proximity and the way the quantum channels between them are set up. Now, it requires cryogenics, and this is the very, very energy consuming for one, but very, very expensive part of most quantum computers, not all. Photonics and quantum dots and quantum diamond technology, where it's worked on the nitrogen vacancy center, NVC. They can work at or near room temperature, but superconductive qubits can't. And that's you can imagine that's just a huge difference. It means there'll always be great big huge machines. They won't be able to go into phones, etc. So that's something definitely, worth knowing. And it's not a feature of performance, but it's obviously a huge cost and a huge maintenance, and it's not desirable. But of course, they need to do that to get the superconductivity. So there needs to be no friction against the electron, if you like. So it's just always will be a necessary part of the quantum computer. How big a issue that will be going forward, we'll see. IBM are talking about a 1,000 qubit machine by 2030. They announced this, which might sound a long way off, but it is only 9 years essentially. But again, you can't, as the whole point of this presentation is, we can't judge that machine by the number of qubits. It's depending on how efficiently it will run every algorithm there is, if you like. And Google, of course, achieved quantum supremacy with superconductive qubits. So superconductive qubits have definitely come out the gates the fastest. Whether that will remain is really up to conjecture. And quantum supremacy, and let's assume that it was reached. It's debatable whether it was or it wasn't, but the point is it's on at least a level basis. Was done with 53 qubits with the Sycamore chip from Google. So it's doing very well now. Regetti, they manufacture the quantum computer integrated chips, which the circuit go on. They've just released the Aspen 7, which is a 32 qubit chip. It's available on AWS. They have their own quantum cloud service as well, supporting VQE, which is a variational quantum eigensolver, and quantum approximate optimization algorithm support. And they are both NISC infrastructures, if you like, for working on NISC, noisy intermediate scale quantum computers, because if we wait till developing it till we get to fault tolerant computers, it's well, the whole industry will go broke, I guess. Now let's talk about trapped ions. Operates at room temperature. It uses optical traps, and it operates inside a vacuum. Now the main, as I mentioned before, the Honeywell HO, which has just come out, and I mean, this month, they have an item, a feature rather, called the MCMR Advantage, which is mid-cycle measurement and reuse. And they've really promoted this, and so they should. I don't know how it works, and I think few people know how it works outside of Honeywell, but it means that on a qubit, the whole thing with working with qubits is that they're always, whenever they're processing, they're in superposition, and that's where so they're entangled with other qubits in superposition, and that's where you get the exponential processing. But of course, if you measure it, then it all goes out the window. It collapses to 1 or 0 with equal probability. But this can have a great overhead. But what Honeywell have come up with is you can mid-cycle. So while it's actually working, you can make a measurement and then carry on reusing the qubit. So I don't know how it does that, but it's a very exciting technology. I'm not sure if Honeywell have actually, I've not seen them give a talk on it. Now, maybe they have and I've missed it, but I might do a bit of, I have already contacted Honeywell actually when they first mentioned this about 3 or 4 months ago. And, the gentleman was very polite and talked me through a few things. Unfortunately, I'm no more the wiser, but it's obviously an interesting technology, and it's if that can be scaled up so that it means you can actually make measurements all the time during the processes. I mean, that's very significant. Let's see how that goes. And JP Morgan did a very large comparison of all the hardware, and they cited Honeywell as the company of the future now. Whether The quantum world, I might add, is very reticent about saying which technology will finally win the race. And that's not through being shy, that's a genuine not knowing what's going to come up trumps, excuse the pun. And then you've got IonQ, and my good friend Denise Ruffner has just been appointed vice president of IonQ. So congratulations to her. I know she watches a lot of these presentations and recordings. So if you're watching, Denise, thank you very much and all the best to you. They just come up with a 32 qubit machine, and they're claiming that you remember Moore's law, where the classical computers doubled in capacity every 18 months or so. Well, IonQ are doubling every 8 months for the next few years, and they're working on 3 generations ahead. So again, very, very exciting. And I should have said before, Honeywell are talking about increasing 10 times every year. So if we saw a graph of their potential performance compared to any other, and I mean all of the other brands, they're way ahead. You know, you can take that with a pinch of salt, but that's the way it is. Now, photonics is very interesting. You know, it operates at room temperature, and it's true solid state in as much as it's done by light, by photons, the polarization of photons. So they talk about being able, their scalability is their main issue. And also the communication, the quantum channels between qubits, they don't have a problem at all. It's very flexible. So if you want to put more photons in touch with photons, it's done a lot more easier than on a superconductive qubit. And Xanadu are talking about millions of qubits and their scalability. They have a Q mode, so they call a qubit a Q mode. And one thing they draw on is that optic technology already exists. So we're already using, you know, obviously fiber optics, etc. So we can use a lot of that, and we have a lot of knowledge in optics. So it's had a bit of a bad rap to begin with, but if you believe the stories of its potential scalability in the future, we may see, you know, good things come from here. So keep an eye on that. Now, quantum dots, which is basically where you isolate a one atom of it can be silica in a phosphorus bed, which is what the University of New South Wales are doing. With Michelle Phillips and John Martinez used to be with Google, and John, I hope that's his right name, surname. I didn't mean to check that, but anyway, John Martinez, he he ran the Google team that achieved the supremacy. So at the beginning of this year, he joined up with Michelle Simmons, Australian of the Year. And what they do is isolate an atom of silica in a bed of phosphorus. And then once that atom is isolated, they can then, you know, use it. They can then adjust it in the quantum way. So the controllability and coherence time, and I'm happy for people to disagree with that, but this is, you know, what most of the market is saying is average compared. Remember the others, some were good and poor. They tend to be quite average, but the coherence time is very good with the silicon-based qubit. The silicon-based qubit can, it's not at room temperature, but it doesn't require cryogenics either. And I might mention that the nitrogen vacancy centered qubits are what operates in the quantum diamond technology. Quantum Brilliance in Australia are doing tremendous work in that area. And so they're at room temperature. And I love their focus because, again, they're looking at near-term solutions. So it might not be the fault-tolerant computers of the future, but the solution will be millions of times better than what we have now. So it's very interesting. There's a lot of talk that it's a good solution for quantum memory rather than being scalable in the future. So again, we may have a hybrid of these technologies where quantum dots is used for storage as opposed to the processing. But, you know, that's, it's all, we're all very much at the beginning of all this, and this can all change basically overnight. Now, the topological qubit is interesting. Oh, I put silicon based there. It requires cryogenics, but it's Microsoft's baby. And as I said before, they're working on a very low number of qubits at the moment, but they talk about their scalability. If they can get the majorana to work as it's supposed to work, the noise will be so low that it will be, you know, pure fault tolerant qubits. So the majorana is something that Ettore Majorana, a guy from Spain, predicted back in the 1930s. And there's a bit of a romantic story about that. He went missing when he was on holiday. Some people say the Russians took him or what have you, but he did go missing. But he predicted there would be this particle that was its own antiparticle. So it's like matter and antimatter. We all know matter and antimatter can't touch, which is perfect for noise control. So if the properties of the majorana can be properly controlled, and that's through, you know, topological is the, you know, the different shapes that you can have. But with it being its own antiparticle, it means that the noise will be kept to a complete minimum. So at the end of the day, what have we concluded? Number one is that benchmarking in the quantum world is very difficult to ascertain. And a lot of that's because we can't test it properly and because our hardware is so limited at the moment. Because as I say, we're just entering the NISQ era. So we really need more devices and more quantum applications to run on them to see a difference. And that's the presentation for today. So I know it's a 100 miles an hour overview of the quantum hardware and the different the different high-tech global tech companies and what they're hoping for and how they're doing. But